In this video, we're going to talk about the most common way of proving a mathematical statement, and that is with a direct proof. So the default method for proving a mathematical statement is to write it as an implication, something of the form P implies Q or if P then Q. Then start the proof by assuming the hypothesis P. A proof which assumes the hypothesis and deduces the conclusion is called a direct proof. Let's see some examples. So first, consider the theorem if n is an even integer, then n squared is even. Let's assume the hypothesis. Let's assume that n is an integer and that n is even. Since n is even, there exists an integer k, so that n is equal to 2 times k. Consider n squared. N squared is equal to the quantity 2k squared, which is 4 times k squared, so we can write that as 2 times 2k squared. Now to show n squared is even, we need to show that it's 2 times an integer. Since 2k squared is an integer, it follows that n squared is even. So that was a nice simple one-paragraph direct proof. Suppose we want to prove a statement such as the minimum of a set is unique. Well, one issue is that this statement is not written in the form if-then. It's not written as a conditional statement or an implication. So before you start a proof, what you want to do is try to write what you're proving as an if-then sentence. If you can do that, then you can start a direct proof of it by assuming the hypothesis. Once you have the right start, then a proof proceeds by using any assumption, by rephrasing it, or reinterpreting it into a more useful form. If that more useful form actually turns out to be the conclusion, Q, then a one-paragraph proof is complete. But if simply working with the hypothesis does not directly lead to the conclusion, then the focus has to change to the conclusion. You need to ask yourself, how would I prove this? How is the conclusion proved? Under what conditions is the conclusion true? So let's try to prove this theorem that the minimum of a set is unique. First, we need to rewrite it as an if-then statement. Here's our theorem. The minimum of a set is unique. We can rewrite this as an if-then statement as follows. We can write it as, if m1 and m2 are both minimums of the set S, then m1 is equal to m2. Okay, now it's of the form if-then, so we can start a direct proof by assuming the hypothesis. So let's assume that m1 is a minimum of the set S. So we know that m1 is an element of the set S, and if S is an element of S, then m1 is less than or equal to S. Assume m2 is a minimum of the set S. Then m2 is an element of S, and anything in S is greater than or equal to m2. We know that m2 is in S, and that m1 is less than or equal to anything in S, so it follows that m1 has to be less than or equal to m2. Also, we know that m1 is in S, and m2 is less than or equal to anything in S, so it follows that m2 is less than or equal to m1. Therefore, we have that m1 is less than or equal to m2, and m2 is less than or equal to m1, so it follows by trichotomy that m1 is equal to m2. So we proved this statement that the minimum of a set is unique by writing it as a conditional. We rewrote it as, if m1 and m2 are both minimums, then m1 is equal to m2. We were able to prove that by writing the hypotheses, reformulating them, using them together, and eventually deducing the conclusion that m1 is equal to m2. Let's consider the following theorem. If n is an odd integer, then n squared is odd. Here we want to be a little bit more careful than we were in the proof that if n is even, then n squared is even. Notice that if we want to prove this, we need to show that there is an integer j, so that n squared is equal to 2 times j minus 1. Okay? So we want to see this as a proof that something exists, that an integer with the right property exists. To prove that something exists, we usually need to find it or build it outside of the proof. So this is going to involve some ingenuity, it's going to involve some trial and error, it's going to involve some scratch work that you don't want to include in your proof. In the proof, once you've found it, then you want to explain why it exists, show that it exists, and demonstrate that it works. Let's try that in this case. So if n is odd, then we know n is going to be 2k minus 1 for some integer k. If we square that, we get 4k squared minus 4k plus 1. Alright, so now n squared, if we want to show it's odd, we need to show it's of the form 2 times j minus 1. This doesn't quite work. So let's do a little bit of work, reformulate this with algebra and see if we can get it in the right form. So we can write this as 4k squared minus 4k plus 1. We can factor out a 2, and that'd be 2 times the quantity 2k squared minus 2k plus 1. And then we don't want plus 1 though, we want minus 1, so we can add a term into the parentheses, a 1 there, and then you can see that actually 2 times that quantity 2k squared minus 2k plus 1, all of that minus 1 actually does give you 4k squared minus 4k plus 1. So it looks like we found our j. Alright, it looks like we found the integer that's going to work for us, because clearly 2k squared minus 2k plus 1 is an integer. So now we're going to use this in the proof. So here's our theorem that we want to prove. If n is an odd integer, then n squared is odd. So let's assume our hypotheses. Assume that n is an integer and assume that n is odd. So by definition of odd, then there exists an integer k so that n is equal to 2 times k minus 1. Let's let j be 2k squared minus 2k plus 1. Alright, so this is an integer. Since k is an integer, it follows that j is an integer. And it works. 2 times j minus 1. If we do all that algebra in reverse, we get n squared. And so we've proved that there exists an integer j, so that n squared is 2 times j minus 1. I should say j, not k prime. And so by definition, n squared is odd. Now, we have many theorems that also help us when we need to show that something exists. So existence proofs, we need to build something, you need to show that something exists. But we do have some theorems that can help us do that. Okay? We have the well-ordering principle, which says that every non-empty set of natural numbers has a least element, a minimum element. We have the average theorem that says that in any ordered field, you can find an element between two elements of the ordered field. We have the division algorithm that says if you want to divide two natural numbers, there exists an appropriate quotient and remainder. The completeness axiom tells us that non-empty sets of reals that are bounded above have a least upper bound. There's the Archimedean principle that tells us that given any real number, we can find a natural number larger than it. And there's a density theorem that says that between any real numbers there exists a rational number. These are really helpful. These are important theorems. They tell us that something exists from not very many assumptions. And any theorem that makes something appear from a few simple assumptions is worth remembering. It'll be really helpful in proofs. So let's try applying one of those in a simple case. So let's prove this theorem. The set S that consists of all real numbers that are of the form n cubed plus 34n plus 9 for some natural number n. We'll claim that set has a minimum. So let's let S be that set. Notice that if x is an element of the set S, then x is actually going to be a natural number because addition and multiplication keeps natural numbers in n. So first we observe that S is actually a set of natural numbers, not just real numbers. Notice also that it's a non-empty set of natural numbers because, for example, if we just put 1 in for n, we get the number 44 out of the polynomial. So we know 44 is an element of the set S. And therefore S is a non-empty set of natural numbers. And so the well-ordering principle tells us that S has a minimum. So we proved the theorem. We don't have to go out and find the minimum of the set. We just know the minimum exists because of the well-ordering principle. Okay, so that's the power of those theorems that tell us when things exist, is that we can apply those and it saves us a heck of a lot of work. So that's it for this video, looking at some elementary direct proofs, giving a little bit of strategy for proceeding in a direct proof. Thanks for listening.